Welcome to EDU World Space.
In this problem, we have a robotic arm that is extending such that when t is equal to 3 seconds, its radial change is defined by 1.5 feet per second. Its current radius at t equals 3 seconds is 3 feet. Its z height is defined by 4t squared feet, and the angle it makes, theta, is defined by 0.5 t radians. What we want to find here is the magnitudes of the velocity and acceleration. I've written out the expressions for these vectors. Since each component vector is at a right angle with every other component vector, we can find the magnitude of each vector by square rooting the sum of each component squared. In order to get those, we'll first need to substitute in all of these dots and variables we have here. So we have everything we need except for z dot, z double dot, r double dot, theta dot, and theta double dot. We'll start with r double dot. R double dot, or the second derivative with respect to r, is just going to be 0, since the robot has a constant radial velocity for that time. Z dot is just going to be the derivative of 4t squared with respect to time, which is 8t, and then z double dot is going to be the derivative of that again, which is 8. Theta dot is going to be the derivative with respect to time of 0.5t, so that's just going to be 0.5, and theta double dot is going to be the derivative of this again, which is 0. We can plug in for z dot of t, since we have a specific time for this of 3 seconds, so that's going to be 3 times 8 is 24. And now that we have everything, we can begin plugging things in. So our dot is 1.5. Theta dot is r, which is 3 times theta dot, which is 0.5, and z dot is 24. And if we want to find the magnitude of the velocity, it's going to be all of these individual ones squared, and then the square root of that. So we can go ahead and plug that into a calculator. 1.5 squared plus quantity 3 times 0.5 squared plus 24 squared power 0.5 to square root it gives us our magnitude of our velocity v is about 24.1 feet per second. So that's great. We have our velocity. That's part of what we're looking for, or we have our speed, magnitude of our velocity. And now we want the magnitude of our acceleration, which is going to be a little bit trickier. So just looking at this formula, we have quite a few double dots here. This r double dot is 0. This theta double dot term is also 0. So we have that this is going to be minus r dot, which is 1.5 times theta dot squared, and theta dot is 0.5 squared, and then all of that squared again, so this minus sign is going to be gone, plus 2 r dot, which is again 3 So 2 times, or excuse me, is again 1.5 times theta dot, which is again 0.5, or excuse me, this r dot should just be a regular r dot. So this shouldn't be 1.5 here. This should be 3 there, and this 0.5 is squared again. Then all of that squared again. Excuse me. Plus z, which is 8 squared. And all of that square rooted, and this will give us the magnitude of our acceleration. So we can go ahead and plug that all in. So that's quantity 3 times 0.5 squared, plus quantity 2 times 1.5 times 0.5 squared, closed quantity squared, plus 8 squared, and all of that to the power of 1/2 to square root it. And we'll get that this is about, the magnitude of our acceleration is going to be approximately 8.1 feet per second squared. And that's the solution to our problem.